Welcome to National Semiconductor's WEBENCH Power Designer and Simple Switcher Controller Technical Training. Hello, I'm Ralf Regenhold, the Power Management Technical Marketing Manager. I'm based in Fürstenfeldbruck, National Semiconductor's European headquarters.
And I'm Jürgen Kühnel. I'm responsible for technical training. The agenda for this seminar is we talk about the Simple Switcher controller family. That includes the new WEBENCH Power Designer that first time enables simulating and selecting of external components, not only resistors but transistors. It is the introduction of the LM315x family. We'll describe the constant on time and the technical background of it and what it means to you. And we show the new design tools that are outside of the WEBENCH Power Designer available for this family. In this family of new power products and tools belongs not only the LM315 Synchronous Simple Switcher controllers, which is covered in this seminar, but also, and you see that here on the left-hand side, the 5th generation Simple Switchers. They are covered in a separate seminar. And we will cover here today the new WEBENCH Power Designer that enables FET selection for the first time in WEBENCH history. The Simple Switcher controllers on the right-hand side seen here, they are constant on-time architecture with emulated ripple mode, and we will explain that in detail. Their advantage is very low bomb count, and they don't need any compensation. They are high efficiency. They are very low output ripple, although they are constant on time. They are available in fixed and adjustable switching frequency versions. They are stable with low ESR output caps, so you can use ceramic capacitors with these. And the solution size of that whole Simple Switcher controller is a very small solution. Let us start with the new WEBENCH Power Designer. For those who know the old WEBENCH, they will be seeing a very new visual interface and additional features added that were not available before. To calculate a synchronous switching device, in this case a controller with external FETs that can be seen here and there, it took all these formulas that we show on this slide to calculate inductor and ripple current calculations, to do component selection, to do MOSFET selection, electrical simulation, stability analysis. All these formulas were necessary to do a good design. Today there is WEBENCH. This is a screen of the new WEBENCH Power Designer that shows after you have selected the product you want to simulate with, and it gives you a summary of everything that you need to know about your design. Let's go from the top left corner, optimization tuning. Here you select between footprint and efficiency. Basically that's a compromise. Higher efficiency, larger footprint. Smaller footprint, lower efficiency. To the right, you have various charts to choose from. In this case, we see here efficiency curves over output current. Next one to the right is the schematic. Here you see what external components have been selected and the components that are needed. Then in the optimizer on the right-hand side, you see curves that show you the various stages that you can select from 1 to 5 with the top left optimization dial that lets you choose between size and efficiency. Left hand on the low side, you see your input data. In this case, 6 volts to 24 volt input range, 5 volt 10 amps output. Next to the right, on the lower, you have your operating values. So here you see all the currents, the heat, everything that you need to know about your design. And then further to the right, you see the bill of materials. Here all the components are described that are chosen for this project. Low hand right, your complete design. You have here all the schematic files. You can download the Gerber files, assembly documentation, design documentation, and you can also go into Altium Designer Viewer editions. So that is the overview window that we offer. Here we show you some of the charts that are available. Top left is an efficiency chart, is from a different design, and it shows efficiency over output current, as before. To the top right, you see, for instance, a VOUT peak-to-peak chart that gives you basically data about the ripple on your output voltage. These are optimization charts. With the optimization dial shown here, you can choose in 5 steps your optimization, and basically we talk about efficiency over footprint. And that is also shown in this chart here. Dial sits on 3, this is where the yellow bar is. And you can see here that once you go to the right hand side to 4 or even to 5, yes, you increase efficiency, but you also increase your footprint. That's here to be seen in one glance. You don't even have to dial. You can say, okay, number 4 is the best that you can get. Apart from the optimization charts, WEBENCH also offers the complete BOM, where you can select alternate parts if you don't like that particular capacitor. It shows you the FET selections it has done for always the low side and the high side FETs over here. You can choose which pair is best for you. And then you can go and do electrical simulation, so like the switching curves here, and you can even go and do thermal simulation. And that shows you where the hot spots on your board will be. Last not least, you can choose whether you want to order a kit of all the materials and a board to do a quick assembly and to go into test right away. That takes for Europe something like 3 to 4 working days. Plus you have the opportunity first time to print out all your design summary, that is your input values, the schematic, the bill of materials, and all the curves that you have chosen on the screens to be shown. Those who you chose not to be shown will not be on the design summary. As mentioned before, the new simple switcher families that are introduced these days consists of 2 families. It's one, the simple switcher 5th generation, covered in a separate seminar, and the LM315x family that we cover today. The simple switcher controller family is power-wise, and it is an extension of our standard simple switcher family to higher currents. Why would anybody use a controller? Yes, they give you flexibility for higher load current designs, but they are very hard to design with, and it's time consuming, especially when you try to optimize the high efficiency curves to select the right FETs. That is why National introduces the new simple switcher controller family. They are very easy to use. They come with a complete solution package. They are very low in BOM count, and WEBENCH and the other tools we offer do most of the jobs for you to make your life easy. Traditional controllers like our LM5000 series or LM315x series or any other manufacturers are not easy to use. It needs an expert. But they can give you high currents, 20 amps, 30 amps, no problem. If you want an easy design, you can choose modules. But the problem with these is they come in certain selections and they are expensive. Our simple switcher regulators, so the 1st, 2nd, 3rd generation of simple switchers, and also the 5th generation we are just introducing, cover that range from easy design to a bit harder design up to 5 amps. The gap that we have up to higher amps, this is the area where the simple switcher controller comes in. They are rather easy to use and they can be used up to 12 amps. The Simple Switcher controller family is a family of 10 products. Output currents can range up to 12 amps. The input range is from 6 volts minimum to 42 volts maximum. And we have available fixed and programmable versions. They are power-wise. At 10 amps you can reach efficiencies up to 93%. That means you have less power consumption and less heat on your board. The applications that we are looking for are projects where time is an issue and applications where you have to supply an intermediate bus, like from 24 volts to a 5 volt rail. Let's take a look at the specs and the features we offer. This is an overview of the 10 parts that are offered in this family. All have the same ratings, up to 12 amps, absolute maximum voltage input 50 volts, and they all have the same TSSOP 14 package. The first in the line is the 3150, which is adjustable. That is only one part. Goes down to 0.6 volts and can be adjusted up to 1 MHz. Depending on the frequency and the range of input voltage to output voltage, you can use it up to 42 volts. All the other parts are fixed. We have versions with 250 kHz, 500 kHz, 750 kHz. And you will see here that in this part, for instance, we have an operational VIN of 33 volts. What is it? We have an output voltage of 2.5 volts at 500 kHz. Due to the constant on-time architecture, there is simply not enough off-time to have a higher operational input voltage than 33 volts. So from 40 volts you cannot reach down to 2.5 volts at 500 kHz. Simply not enough time internally. That is the limitation. The part withstands 50 volts absolute maximum rating, no problem, but operational 33 volts. And that's the same for the other parts, like the 750 kHz parts that do not reach the 42 volts operational. Shown on this slide is the external components needed. For the adjustable, due to the fact that it's adjustable, we need a few more components than with the fixed version. The adjustable needs the resistor divider here, and it needs the R-on to set the frequency. All the other components are the same. So we have 11 components for the fixed versions and 15 components for the adjustable versions. This makes very small solution sizes.
This slide shows the block diagram of the LM315 embedded in a synchronous buck regulator. The input voltage charges the input capacitor. This is the energy reservoir for the buck regulator. From there, the energy is transferred via the high side MOSFET into the inductor. From there, the energy is transformed into the output capacitor. The actual voltage of the output capacitor is determined by the duty cycle of the high side and the low side MOSFET. The output voltage is sensed by the resistive divider and is fed into the error comparator. It is compared to the internal voltage reference. From there, the result is fed into the logic circuitry, and this controls the duty cycle of the low side and the high side MOSFET driver. The high side MOSFET is an N-channel type and needs a bootstrap capacitor to supply the high side driver. The device uses a low voltage internal voltage rail generated via LDO. This is buffered by a small output capacitor. The peak current in the inductor can be programmed by an external resistor. This block is the emulated ripple mode circuitry, which allows the use of low ESR output capacitors. This will be explained later. As the device is able to supply up to 12 amps of output current, it needs an external soft start capacitor to program the soft start time. This prevents an overshoot of the output voltage during the startup. This resistor sets the on-time of the constant on-time circuitry, which actually programs the switching frequency of the controller. This slide shows the block diagram of the fixed frequency and fixed output voltage device options. It saves 5 external components. The resistor to program the peak current is saved, as the peak current is set by the RDS on of the low side MOSFET. The resistive divider to set the output voltage is saved, as we have fixed output voltage options. The resistive divider is transferred into the device. The external soft start capacitor is saved, as the soft start is realized to an internal soft start circuitry. The external R-on resistor is saved, as it is transferred to an internal R-on, which gives a fixed frequency.
The summary shows where the advantages of that new family are to be found. First, we have the WEBENCH simulator that lets you select the components, including the external FETs. It lets you electrically and thermally simulate your design. Then we have the constant on-time regulation that is used in this part. The advantage of that is it does not need any compensation, so that part is stable under all conditions, and it reduces the bill of material count, so the component count, to make a small design. We have the adjustable product, the LM31550, that lets you choose odd output voltages that are not offered in the standard versions, and it lets you choose the frequency. Like you want 300 kHz, you can adjust it. The fixed versions, however, makes the smaller size solutions because they don't need external components like resistor divider and an additional capacitor. Reduces the size by 4 components. Their power-wise, efficiency of 93%, 95% is easily reachable. And they all have the same input voltage range from 6 volts in to 42 volts in.
On the next slides, I would like to give you an overview of the constant on-time regulation and the emulated ripple mode circuitry. To understand the advantage of the constant on-time regulation scheme of the LM31550, let's have a look at the basic voltage mode PWM DC-DC converter. Its output voltage is sensed via a resistive divider and is fed into an error amplifier. There it is compared with a reference voltage. The bandwidth of the error amplifier needs some limitation. This is done by an external compensation circuit. This is needed for loop stability. The error signal is compared to a fixed frequency sawtooth from an internal oscillator. This results into an overall rectangular fixed frequency waveform, but the on-time is adjusted by the error of the output voltage. In total, the advantages of the voltage mode is to have a fixed frequency, low ripple at the output. The disadvantage is this fixed frequency, together with a limited bandwidth, results in a slow transient response. Now let's look at a hysteretic buck regulator architecture, which is the basis of the constant on-time used at the LM31550. The output voltage is again sensed by a voltage divider and fed into the error comparator. This is comparing the voltage to an internal voltage reference. There is no bandwidth limitation of this error comparator. As a result, you get a hysteretic waveform, which is rectangular, and the on-time of this is lasting as long as the output voltage is below the reference threshold, and the off-time is dependent on the discharge time of the output capacitor below the reference threshold voltage. This explains why there is a minimum ripple needed at this point at the entrance to the error comparator. Now let's look at the advantages of hysteretic buck architecture. The wide bandwidth means a fast transient response during load changes. No frequency compensation is necessary, no poles, no zeros to deal with. VIN feedforward is inherent, which means at higher input voltage the on-time is automatically adjusted to shorter time. Let's look at the disadvantages. The T-on and the T-off time are not constant, and therefore the frequency is not constant, and it is a function of several parameters. One of them is input voltage, then output voltage, load current, inductor value, ESR of the output capacitor, ESL of the output capacitor, the actual hysteretic voltage of the error comparator, and the TD, which is the internal delay time of the IC. So in summary, frequency is difficult to control. Finally, we arrive at the block diagram of the architecture of the LM315, which is a constant on-time hysteretic. A simple block diagram has been added. It generates a one-shot on-time, which is inversely proportional to VIN. This is achieved by the on-time setting resistor connected to the input voltage. So for a given VIN, the on-time is constant, even if the load current varies. So overall, the addition of the constant on-time block results into a constant frequency operation. In addition, the constant on-time provides high efficiency at light load and fast transient response at load changes. A disadvantage of the hysteretic regulation is the requirement of a minimum ripple at the feedback comparator. Output noise may add disturbance to the comparator input ripple through the resistive divider. These problems are avoided at the LM315 by the emulated ripple mode technique, which I will explain later. Now let's have a closer look into the details of the constant on-time regulation. The output voltage is translated to the feedback voltage by the resistive divider. When the feedback voltage is lower than the reference voltage, the one-short circuitry sets a fixed on-time. Let's have a look at the switching node. Here we see the timing diagram of the switching node. During the on-time, the switching node is connected by the MOSFET to VIN. During the on-time, the inductor current is rising linearly. The voltage at the output capacitor is increased accordingly. The feedback voltage is tracking the output voltage. Now let's look at the off time. Once the on time is terminated, the MOSFET switches off and the switch node reaches its low level. During the off time, the inductor current is falling. The voltage at the output capacitor is falling as well. The voltage at the feedback pin is still tracking the output. The next on cycle will not be initiated before the feedback falls below the reference voltage. Overall, we end up with a fixed frequency with a duty cycle dependent on the ratio between the input and output voltage. On this slide, I would like to demonstrate with the help of some simple formula how the constant frequency is achieved when using the input voltage feedforward technique. Let's start with the definition of the duty cycle. D, the duty cycle, is equal to T on, which is the on time, divided by T, the period. This equals to T on times the switching frequency. Let's call this equation number 1. There's a second equation for buck regulators. The duty cycle is defined by VOUT divided by VIN. Let's call this equation number 2. If we set equation number 1 equal to equation number 2, we get this term. T on times the switching frequency is equal to VOUT divided by VIN. Let's record this as equation number 3. Another formula for constant on time with feedforward is this one. T on is equal to K, which is a constant factor defined by the IC designer, times the R on, which is the resistor connected to the VIN, divided by the VIN input voltage. This is equation number 4. Now, if we insert equation number 4 in equation number 3, we get this term. This term can easily be solved for the switching frequency, and we get to the final formula, which is the switching frequency is equal to the output voltage of the regulator divided by K, the constant, times the R on resistor. So we see we get a switching frequency which is completely constant, independent of a current or independent of an input voltage. Of course, the VOUT is constant as well because we regulated it. So the R on sets the constant frequency. This slide shows a practical measurement of the switching frequency over a very wide variation of input voltage. The deviation of the frequency is only in the 1-digit percentage range. So under normal working conditions, the input voltage will vary less. So the regulator will always work at a constant frequency. The LM315 uses a technique called emulated ripple mode, which does not need a ripple at the output. In order to understand that, we need to start looking at a standard constant on-time regulator, which needs a certain minimum ripple at the output. The constant on-time regulator regulates by comparing VOUT through the resistive divider with the reference voltage. At this node, there must be a minimum ripple so that the error comparator is triggered correctly. VOUT must have a large enough ripple in order to still be enough at this node after being divided by the resistive divider. The ripple at the output is generated by the current in the ESR of the output capacitor. The ESR of the output capacitor must be large enough to create sufficient ripple at the output to still properly switch the error comparator. So we just learned that a standard constant on-time regulator needs a sufficient ripple at the output. How can we influence that ripple? Let's look at the buck regulator waveforms and the mathematical formulas. The first row on this slide shows the waveform at the switching pin. The second one shows the current in the inductor, and the third one the ripple of the output voltage, which is the one who's mostly interesting for us. This is the voltage of the output ripple. This amplitude is actually the voltage across the output capacitor, and it's called delta VOUT. So delta VOUT is equal to two terms. A first term, which is the delta of the inductor current, times the ESR of the output capacitor plus a second term. The first term is the one who influences the ripple the most. It consists mainly of the ESR of the output capacitor. So by choosing this value, you can mainly influence the ripple of the output. The second factor is the inductor current. The inductor current ripple is determined by this formula. It's dependent of the delta of the input voltage and output voltage. This term is fixed, and two other factors. One is the on time. The on time can be chosen by selecting the right on resistor. And there's another factor contributing. It's the inductor, which the designer can also choose. So these two, the T on and the L, give you the value of the inductor ripple. So the second term at the output ripple voltage is the one who can cause problems. We will talk about these problems on the next slide. This factor only comes into play if the ESR is very, very low. Example, ceramic output capacitor. Only in this case, and also with small values of the output capacitor, this factor influences the ripple and can cause some problems. So what happens if the ESR of the output capacitor is too small? From the slide before, we learned that the output voltage ripple is dependent of a ESR related voltage and a capacitance related voltage. This capacitance related voltage is phase shifted 90 degrees from the inductor current waveform. The ESR related voltage is in phase with the inductor current waveform. So if this ESR is small, then VOUT would be dominated by the phase shifted capacitance related voltage. This is causing the switching voltage to jitter and the circuit to regulate poorly. The timing diagram below shows the output voltage ripple under two conditions. The pink one at a high ESR with a stable regulation. The black one with a low ESR, sinusoidal ripple waveform with a poor regulation and a jitter. So for stable regulation, output voltage ripple amplitudes of up to 100 millivolts could be necessary. This could only be achieved with high ESR values. But this means it may not be acceptable such a high voltage ripple at the output for all applications. With the LM315 Simple Switcher controller, National Semiconductor introduces a new patented technology called emulated ripple mode at constant on-time regulators. This eliminates the need for large output ripple even for stable regulation. This eliminates then the need for high ESR output capacitors. So it allows the use of smaller, less expensive ceramic capacitors. So how does that emulated ripple mode work? Here you see again the block diagram of a constant on-time regulator. The blue arrows indicated the current loop during the off time. We have a current circulation through the output capacitor, the MOSFET, the inductor back to the output capacitor. This is the MOSFET with the switch and the RDS on. This is the output capacitor with its internal ESR, which would be located here. A big ESR would generate this kind of output voltage ripple. An output voltage ripple here is not preferred. So how can we get rid of this ripple? We take the ESR and move it in the closed loop to this position here. There we can still take the voltage across this resistor and use it for regulation. But we avoid any resistor in series here. So we have a small or no resistor in series with the output capacitor. So we have almost no ripple at the output. This is exactly what we need. Now let's look at the voltage regulation. The output voltage is sensed and fed back to the comparator and compared with the internal reference. The sinusoidal waveform here is coming from the fact that the output capacitor has no ESR in series. This is not causing a stability problem because the signal is not compared with a DC reference, but with a DC reference plus the ripple voltage across the RDS(on) of the MOSFET. So basically, we remove the undesired ripple from the output and reconstruct it at a place where it does not hurt us, the RDS(on) of the MOSFET. This means emulation of the output ripple, or so-called emulated ripple mode. Let's have a quick look at the emulated ripple mode circuitry in the IC. It is located here. It detects the voltage across the low side MOSFET. This voltage is added to the internal voltage reference and fed into the error comparator and compared to the voltage at the feedback pin coming from the resistive divider from the VOUT, the VOUT across the output capacitor having no ESR. The new emulated ripple mode constant on time allows the use of ceramic capacitors at the output. The benefits of such a ceramic capacitor are a clean output voltage, which means a low output ripple. This is comparable with voltage mode and current mode control schemes. Another benefit is the low profile and the small size of the ceramic capacitors. It can reduce the output ESR by a third and save PCB area. A ceramic capacitor is in addition not sensitive to transient voltage stress. This means a higher reliability. And at the last point, there's no polarity. It's easy for production flow. Let's compare the output ripple voltage of two different buck regulators. On the left side, a buck regulator with a tantalum output capacitor, which has a high ESR. So the ripple voltage is quite big. On the right side, a buck regulator with ceramic output capacitor, which has a low ESR. Here you see the significant difference of output ripple voltage at the same capacitance. So in summary, the emulated ripple mode enables the use of low ESR capacitors while still maintaining proper regulation at constant on-time scheme. So after all that explanation, I would like to summarize the advantages of constant on-time with emulated ripple mode as used in the LM315. No loop compensation is needed, which means a low external component count and an excellent transient response. So you can achieve lower solution cost, ease of use, and a reliable design. The constant on-time with voltage feedforward guarantees a relatively fixed frequency operation. This leads to a reliable and robust operation and makes the design easier. The emulated ripple mode circuitry gives you a low output voltage ripple while still maintaining regulation. It allows the use of low ESR output capacitors without additional ESR compensation. Lower ESR caps means smaller size, reliable operation, and flexible design.
Let's take a look at the design tools we offer. Apart from the new WEBENCH Power Designer, we offer Excel calculators for offline work. There is a quick start guide and there's a MOSFET selector. Then we have reference designs, and for the reference designs and demo boards you can get the Gerber files. The same with the evaluation boards. Also Gerber files available. Plus we have application notes. The Excel tool for the FET selection offers you this view. You basically enter your data here into the blue fields and you can select a high side and a low side FET already. Then you go Start Calculation and the Excel tool will now calculate, showing the user selection, so what you selected, and it will show what it the system recommends. And then you can decide whether you want to go with that part proposed by the system or your own part. And it will give you a chart that shows you, okay, high side switching, high side conduction losses, low side conduction losses, low side diode conduction, and so forth. So it lets you see how good is your own selection compared to the recommended selection. This is the component selector chart. Again, you enter your data into the blue fields, here, down there, and this then gives you the bill of materials. This is offline. You can do that on your PC without having to have internet connection. To make life even easier, we offer the reference designs. If one of these fits your application, you can simply take the Gerber files and copy and paste it into your own design. To download datasheet or the Excel tools or anything else like an application note, simply go to national.com/switcher, the homepage of our Simple Switcher family. Thank you for spending time to look into the new Simple Switcher family of National Semiconductor. Goodbye.